just about a year ago, he moved to Santa Cruz and joined the UC Santa Cruz, the FRB team there as a project scientist. And so today, Lluís will tell us about CGM cloud sizes from FRB scattering. Let's welcome him.
Thank you, Juan. Thank you all for coming and for having me. Yes, I'm going to talk about a recent project that we just finished and we put on archive last week. So if you check it out and you see something wrong, please let me know. We have still time to correct anything. So I'm going to talk a little bit of a new thing that I started working in the last year, which is this FRB business, which is something very popular and which Taiwan is going to be one, if not yet, one of the leading world institutions with the burst instrument. So let me start from the beginning. So let's talk a bit about galaxies. My main focus is not the FRBs themselves, but the galaxies that we can probe with the FRBs. So let me give you a brief, very cartoon introduction about the galaxy. So what we usually call the galaxy is this thing in the center here. Here is where the stars are, so this is what we see when we look at the sky. But the galaxy, if we want to study the evolution and the formation of galaxies, we are also concerned about what happens around this central part here. And this is what we call the circumgalactic medium, which is this gas component that is extending several hundreds of kiloparsecs away from the center of the galaxy. And this part is interesting for the life of the galaxy because it's where fresh gas from the intergalactic medium is accreted through gravity towards the center. And this gas will be used to produce new stars and continue the life of the galaxy. And at the same time, these stars, when they die, after producing metals, they explode and they eject and enrich the surrounding gas with these metals. So it's kind of a life cycle, and you can see it's a galaxy coming in and then galaxy going out again. So it's a process of interaction between the galaxy and the more distant intergalactic medium. So I want to use FRBs to try to study the circumgalactic medium. And this is because there are no stars here, so this gas is not bright, so we need to find other techniques for doing that. It doesn't work. All right, so let me tell you a bit more about the circumgalactic medium. So the circumgalactic medium is a multiphase medium. There is hot gas, most of it low density hot gas, and inside, in the middle of this dense gas, there is colder and higher density gas. The colder one, usually it's the fresh one coming in from the IGM, and the hot one is usually produced by gravity energy and also from the feedback from the central black hole and these stars that are exploding. But the cold gas in particular, at about 10,000 Kelvin, is interesting because it has some properties such as the density and especially the cloud sizes that give information about the physical and thermodynamical processes that happen. So if we want to understand the CGM and we want to know which physical processes are at play, one way to understand this is by looking at the properties of the density and the clouds. For example, if you have gas that is at very high density, that possibly indicates that there is a low temperature, and the opposite. Or if you can form clouds of very small sizes, you need some physical processes that maybe break big clouds in smaller pieces. Or if you only have cloud sizes in a galaxy that are very big, then maybe you can think, oh, maybe there is not much turbulence happening, because if there was turbulence, it would break. So I will try to connect these observables that we can try to infer, I don't want to say measure, but we can infer with the physical properties that explain and drive the circumgalactic medium. And I want to do this, or we want to do this, with FRBs. So the way we play this is very similar to what has been done for many years with galaxies and with quasars as well. So we are here, and then on the other side, we have a very bright light source. And the light of this source goes through some circumgalactic medium, some galaxy. So it's affected by this medium. And then when we are here, we look at how is this light affected, and from that we can extract information about this. Okay, so this is our goal here. We want to obtain information about this circumgalactic medium by looking at the impact on the FRB signal. Okay, maybe first of all I should say what an FRB is. I think I don't need to say it very clear here or very extensively because most people know. I will just say that it's a very bright and very short pulse in the radio band, mostly curved, and it's produced by a stellar object. I, on purpose, try to be super vague here. I don't want to get into trouble because this for me is a tool, so I don't know anything about FRBs, and I think it's not very clear yet what FRBs exactly are, but I will just shoot the word magnetar in there, and then you just decide if it's correct or not. So I will just say that it's a bright flash in the radio, and that's all I need for today. How do we observe the FRBs? So here we have it's called sometimes a waterfall plot. So here we have the spectrum. In many ranges of astronomy, we only observe this thing here, but because this FRB duration is finite, it's a transient event, we also care about the time, because it starts at some point and then it finishes at some point. It's not like a quasar that is on for longer than the lifetime, our lifetime, for sure, so it's kind of a constant. This thing, we care about its duration. So a couple of observables here. The first one is this one here. So we observe the universe, there is nothing, and at some point a flash appears. And when this pulse appears, then starts going away, fading away very slowly with a slow decay. This part here is what we call a pulse broadening. And what is causing this is the light from the FRB goes through some material, and when it goes through this material, scattering happens. So different rays of light travel different paths. And when they arrive at the observer, depending on if the path is very long or very short, they arrive at different times. So most of the light arrives at a certain position, but some other paths have taken, some other rays have taken other paths, so they arrive later. So this is kind of a diffusion, if you want, of the light of the FRB arriving at the observer at different times. So this already gives us some information about the material that is in between us and the FRB. So the images are scattered, they have different paths, and they arrive at different times. And this is very, can be well characterized. It has a clear frequency dependent. And this is what we call a pulse broadening. It's kind of an extension to the tail of the pulse. The other part is when we look at the spectrum in here. And this is what we call a scintillation. So these different rays that take different paths, they can interfere with each other when they arrive at the observer. And if you imagine the interference of waves, sometimes these interferences are constructive, so you have more signal. Sometimes they are destructive, so you cancel the signal. So that's exactly what you see here. Fluctuation in the intensity. Some very bright spots, and some darker spots. So this is the interference of these different paths. So these are two very typical, I would say, or common observables for FRBs as well as for pulsars when we are in the Milky Way. So let me say something more about this circumgalactic medium that is in the middle between the FRB and the observer. So this is the FRB cartoon, which by the way is a paper, a student working with Wei Li here from a couple of years ago. So this is the FRB, and the light from the FRB is propagating and then intersects this green thing here, which is the Milky Way. When different path rays or different rays intersect the Milky Way and they are scattered, they are redirected and they go to the observer, and these different paths again interact and create this interference pattern. So here you can see again bright and dark spots, fluctuations in the intensity. if you assume, this is just, if you assume some finite resolution of your instrument, if your resolution is very high, you can see this very clearly. If you have a not very fine resolution, you will have a smooth version of this. Not super important here. But what happens if there is another galaxy in the middle, which is the one we want to study? So this is the case. So now we have the FRB, we have the Milky Way, us, and here we have another galaxy. One circumgalactic medium, one halo. What can happen, depending on the relative position between these three guys, and depending on the physical properties of the gas in here, what can happen is that these rays will be scattered here, and then they will be scattered again here. And this fluctuation pattern that we saw initially actually can be much more choppy, can be cut in small pieces. And then if we have very good resolution of our telescope, we can see all the thin spikes. But if the resolution is not very good, then we just wash out the signal and we don't see anything. So basically, depending on the physical properties of this and the relative position of the different objects, it's possible that scintillation disappears. That's the effect we want to use to understand properties of these guys. Any questions so far? Okay. One more tricky thing. I've been saying that the light scatters in the gas and takes different directions and so on. In radio, we can consider two types of scattering, diffraction and refraction. And this is mostly, broadly speaking, characterized by how big is the object that is scattering the radiation. In this case, how big are the gas clouds or the gas elements that scatter the radiation compared to the Fresnel scale. For very small gas clouds or particles that are below the Fresnel scale, this corresponds to things that are smaller than 1 AU if we consider that it's a gas at the 1 gigaparsec distance from us. So this is really tiny gas particles. Then the type of scattering would be diffractive. Usually to create these tiny gas elements, and they need to survive long enough to do something, the way that we can create them and keep them alive is through density, through turbulence. So this is exactly what happens in the interstellar medium, and pulsars have or present or show a lot of diffractive scattering because in the interstellar medium there are turbulent processes that are able to drive these scales to very small and have very small gas particles. In the CGM, it's possible that there is turbulence, well, there is turbulence, and it's also possible that circumgalactic turbulence can create and maintain gas at these scales. It's possible, but it's not very clear or very sure. And actually, I believe it's difficult that it happens. And the thing is because in the CGM, the physical processes and the temperature and densities are much different than the ISM. And I think part of the work that is using diffraction in FRBs is because people work on ISM and they just took it and put it in the CGM. But if you talk to CGM people, they will say, well, we are not sure this type of gas exists in the CGM. It's a bit tricky to handle. So there are many physical processes that can cut off or stop turbulence before it can reach those small scales. Also, observationally, it's really hard to have evidence, measurements of things that are on this scale, so we don't have much support for these things. On the other side, so I'm trying to say it's very difficult. I don't want to say it's impossible, but I think it's very difficult to have that in the circumgalactic medium. But it's possible. On the other hand, we have refraction. Refraction is just big things. As long as you are above the Fresnel scale, you can scatter radiation. And this means things of the size of a parsec, kiloparsec, which are oftenly extracted or inferred from observations, many times from absorption line spectroscopy. And also, these sizes are supported by theory and simulations. Simulations because it's big enough that it can be almost resolved. Those are difficult. And for example, there is the cooling scale or something called a shattering-scale, which is big clouds that a certain temperature, there is a process which is cooling for which they fragment in small pieces. And it seems that they fragment in small pieces and they reach typical circumgalactic densities, tens or hundreds of parsecs. So there is, in this case, there is support that this type of sizes and this type of gas exist from observations and theory. So, as I said before, many people have been adopting diffraction, implementing, but we thought, okay, let's take a deeper look at refraction. And this is similar to the paper that the student and Whaley did a couple of years ago. They also did the same thing. So I'm going to talk about refractive scattering today. So let me just recap. So we want to probe the sizes and densities of the circumgalactic medium of some galaxy that is in the middle between us and the FRB. And we will use refractive scattering because it must exist. We know these clouds are there. They can be bigger, smaller, but they are there. Maybe there is also diffraction on top of this, but I will not care about that today. And depending on if we see a scintillation, yes or no, and what type of scintillation, then we can have constraints on these two parameters here. No questions? If you have questions, please stop me anytime. Okay, let's take a look at the math here. When radiation goes through gas and scatters in different rays that they take different directions, they arrive at different times. So between different images or rays, there is a time delay, a characteristic time delay. This time delay is given by this formula here, which is pretty horrible. But basically, what it's saying is how many clouds you intersect in your CGM. And this is the size, the virial radius of your halo, the size of your clouds, and then what fraction of the volume is full of gas, yes or no. So the number of clouds is important. More clouds mean more scattering, more time delay. And then, let me say a bit more. So here we have the number of clouds. This is the size of the clouds. Here we have the electron density squared. It's an important parameter. So these are our two quantities. And then here we have the distance to the CGM, the distance between the CGM and the FRB, and the distance from us to the FRB, and some redshift. So all this is the geometry, like I said, relative distances, physical properties of the gas, and then frequency. Okay? So this is how we will connect density and size with scattering. There is another thing. If we want to have time delay between images or between rays, at least we need two rays. So there is one limitation here that this scattering needs to produce at least two rays that will converge at the observer. So this is an important point. So the number of images, except for the source image, needs to fulfill this equation, and it has to be larger than 2 or larger than 2. And if you take a look here, we see that the size of the clouds goes to the power of 3. So small clouds will reduce the number of images a lot. So that's not good, because we need 2 or more images. Otherwise, there is no scattering. And the density goes squared, so this is the same value here. And then the geometry factor is also squared here, and here is linear. So this factor, geometric, and especially the size of the clouds, will be very important for how many directions, how many rays converge, how many images we can see. Okay, so this will be a very limiting factor. Okay, so now we can calculate things. If we assume galaxy with some properties and we put it in the middle between us and one FRB, we can see how much time delay we get, how many images we get, and we can see what happens. And this is the result. So here, this is 2D plot of size of clouds. This is one halo full of clouds of a given size. All the clouds are the same size, very ideal situation, and all the clouds have the same density. Okay, and 10% of the volume is full of this cold gas. This is kind of a typical value that we expect for the CGM. Changing this parameter a little bit does not change much the full picture. Okay, so what we see here is high density gas, low density gas, big clouds, small clouds. And here I just put these limits from two papers that it's from observations. This is the cos halos data in blue here, and this red one is for luminous red galaxies, also from cos. And you can see that the typical densities of the CGM gas are between 10 to the minus 2 and almost 10 to the minus 4. This is the most of the gas in the CGM is within this range, most of the gas. So what we see here is this white area. This white area is where, if we have a halo made of clouds of this density and this size, scattering refraction does not produce two images. So basically what this says is that typical gas in the CGM, most of it is not affecting the FRB because there's no scattering, because there are no two images. That's one of the main results. Now, if we go to high density and small sizes of gas clouds, if we have a CGM made of very small clouds and they have high density, then we are in this colored part. And you can see that the scattering time starts going up from the order of milliseconds and above. One other thing here is this diagonal line here. This diagonal line marks the shattering scale. If you guys know what this is the typical size or the minimum size of the clouds that you expect through fragmentation from theory. So I would say that this imposes kind of a limit from pulling what is the minimum size of clouds. So if we go in this area, we can say that, okay, clouds that are around 1 parsec in size and 10 to the minus 1 cubic particles per cubic centimeter, they correspond to the shattering scale, and we can see that if the CGM is made of these clouds, then they will produce a scattering on the order of 1/10 milliseconds. So if the CGM is made of dense and small clouds, then we have scattering. And it's going to be large, so maybe it will impact a scintillation. Is that clear? But most of the CGM gas will not be very important. So this is a bit of a sad point, because I expected the CGM to affect FRB a lot, so we can get a lot of constraints, but now this result is only saying that very dense gas, small sizes will affect. We don't expect a lot of this gas to be in the CGM, and dense gas has to be close to the center of the CGM. So if we want to go through it, we need sightlines that are going through close to the center of the galaxy. Let me just summarize this. Most of the CGM gas, the bulk, the typical CGM gas, will not have an impact on FRB. Only these very dense clouds, that is probably close to the center, will have an impact on FRB. And the impact can be that this scintillation will be cancelled, as I showed you before. Another point that I add this morning here. Or this can also happen in high redshift protoclusters. So at redshift 0.1, 0.2, 0.3, this is the typical gas. This density is the typical gas in the CGM. But when we go to higher redshifts, we expect the density of the gas to increase. So there are objects that are protoclusters, so gas that is around massive galaxies, typically around quasars that at redshift 2 that become clusters at redshift 0. And these guys at redshift 2 have densities that are around this range. So we can look at dense gas in the low redshift, or we can try to look at high redshift gas. But of course, if we go to high redshift, then we need to put an FRB even more at high redshift to intersect. And for now, we have detected redshift 1 FRB is the record. And secret is that we have detected one at redshift 2.2. It's coming soon, but that's a secret, don't tell anyone. But we have one. So if we want to investigate and intersect gas at redshift 2, we need a lot of FRBs, more than redshift 2. So it's going to take a minute. All right. So the only gas that impacts is high density gas and small sizes. This gas can impact the scintillation, but as I said, it's not very high probability to intersect one of those, because we expect this gas to be very central to the core of the galaxy. This is, not much details here. This is just the probability of intersecting this gas with the FRB at certain redshift, and then integrating along the sightline. And this also depends on how much of this gas is covering all that halo, or that central part, I think 10 kiloparsecs. So in any case, you can see that the probability of hitting dense gas, so the probability to impact a scintillation with intervening CGM is pretty low. Just for reference, this type of gas is very similar in properties. The density is very similar to what is called high velocity clouds in the Milky Way. If someone knows about high velocity clouds, this is the kind of stuff we are talking here. So we expect it to be very central, and then it's difficult just to hit it with one sightline. It's not everywhere in the CGM. Okay, but what we can do? We can use dense gas and small clouds. Okay, let's focus on that. And if we go to very high densities, 1 particle per cubic centimeter, that's very high density gas for the CGM. And 0.1 parsec, which is quite tiny, only intersecting one cloud, not one halo or one CGM, just one cloud, is enough to kill the scintillation signal. Okay? So can we use this information to get some constraints on the CGM, only considering this very dense gas? My next idea was like, oh, the dense gas is sometimes connected to magnesium-2 absorbers. Magnesium-2 is an element that is usually located in very high density regions in galaxies and the circumgalactic medium of galaxies. So my idea was like, oh, maybe if we can get information from this scintillation of suppression for these guys, maybe we can say something about the dense gas, and maybe we can connect the dense gas somewhat to magnesium. But there are a couple of questions here. For magnesium, we measure magnesium in absorption lines, for example in quasar spectra, and what we measure is the equivalent width, the area of that absorption. So how do we connect this equivalent width with the density and the size of the clouds? That is model dependent, and there's not one single way of doing that, so it's not straightforward. And then how much equivalent width will correspond to that gas, so scintillation can be suppressed. So these are still a bit open questions. And then when we have a quasar spectrum with some magnesium absorption, we can identify absorption lines, and we call that components. But I'm not sure that one component means one cloud. Maybe one component is many clouds and all this. So to answer this, I decided to go to Taiwan and ask the world expert on magnesium 2 absorption. And we had a chat with Ting Wen this morning, and he clarified me some things. So I think there is still a bit of future here, and we can do more things. But here is the main idea. If I take from the CHIME collaboration, for example, which I'm part of, 1,000 FRBs, and we see that 20% of these FRBs, the scintillation is suppressed. This fraction, I can connect this fraction of suppression to the probability of intersecting one of these, at least one of these clouds, because intersecting one is enough to suppress the scintillation, so I can make this connection. So the fraction of FRBs with no scintillation can give me, at least a limit, the probability to intersect dense gas. And then I can play with the relations between the size of the clouds, the density, and the equivalent width to make a connection with magnesium. So I did some preliminary calculations here. This might change a lot. Again, preliminary, don't take it for sure. This is not in the paper. This is hopefully the next step. So Wan Tun Zhu and Lluís Menard a few years ago calculated from SDSS quasar spectra how many number of absorbers per unit redshift and per unit equivalent width you get when you intersect in quasar sightlines. So you can see here that big absorbers, high equivalent width, less than small absorbers, and also it changes with redshift, and here you have the number. So here we have information, how many of these magnesium do I find for a given sightline, and of a given size, equivalent width, and with a redshift of the FRB. Just some formulas here. And then we don't have yet the information from CHIME. I'm waiting for it. How many FRBs have suppressed scintillation? What fraction is that? Hopefully this summer. Someone is working on that. But for now, as a simulation, I took 500 FRBs and I assume that they are distributed in something called dispersion measure, which is connected to how far they are, somewhat. And I just give the distribution that is similar to the FRBs that we have observed so far. And then given this DM, I can calculate the probability of a given redshift. So then this is a distribution. And then I can sample 500 times here, and I can create many realizations of 500 FRBs. I can take the average of that and the percentiles and whatnot. So I did this, and I did this assuming different equivalent widths limits. And I assume that these equivalent widths, this is a big assumption, I assume that these equivalent widths correspond to the dense gas that can suppress the scintillation, which is probably not true. But I thought, okay, you can see here, I take some equivalent width, depending on what range, almost no FRBs will be suppressed, will not have suppressed scintillation. Depending on what equivalent width, I assume maybe 4% of FRBs, and at most it seems that 10 or 11% of the FRBs can show suppressed scintillation. This is always assuming that that equivalent width corresponds to the dense gas enough. So alternatively, I think, or from the other side, what I could do is I can calculate the fraction, or we can calculate the fraction of CHIME FRBs with suppressed scintillation. Then I just calculate all the possibilities, and the one that matches our CHIME observations can be an indication of like, oh, maybe that dense gas of 0.1 parsec and 1 particle per cubic centimeter corresponds to this range of equivalent widths. This is a little bit the game to try to connect both things. But again, I still have some doubts about how to connect the density and the size with the equivalent widths that I've been chatting this morning with Ting. that is work in progress. So I think, I have no idea what time is.
You have plenty of time for Q&A, but
okay.
free to.
I'll just make another recap summary final, and we can do as many questions as you guys want. So yes, to recap. So diffraction and refraction. Diffraction may exist. It might be difficult to have in the CGM, so we take a look at refraction. This puts a lower limit. If there is also diffraction, it will be on top, so it adds to the total scattering. But looking at refractive scattering, we can have constraints on the density and the size of this cool gas. This is in the paper. This is the theory, so it's clear. And then what we find is most of the CGM gas, unfortunately, seem to not have much of an impact on the FRB signal, so we cannot extract much information. The only one that can impact scintillation and the effect of the scintillation Milky Way is dense gas. So we want dense gas to extract some information. And then focusing on the dense gas, we can try to connect how many FRBs have no scintillation and how much, what's the probability of hitting this dense gas in given sightlines, and try to make a connection to extract either information about the equivalent widths of this magnesium or some information about the dense gas. And I think that's all. Yes, thank you very much.
Questions, please?
It was so clear.
Could you remind me what's the different signature between diffraction and reflection? Or is the same? They will produce the same signature.
So the physics is a little bit different, and the math that you need to use is also different. So refraction is basically just kind of lensing, a geometric effect, so it's very easy. For diffraction, then you need to go back to wave physics and play with densities and interference, so it's more complicated. But the main difference is that diffraction will happen for tiny scatter size, and refraction for anything that is larger than the Fresnel scale. The observable will be the same. So they will both produce multiple images and have the same effect. Now, if you have the same, say that you can have both, and you have the same physical properties of the gas, it's typical that diffraction will produce a bit more scattering than refraction. So considering refraction alone, it's kind of a lower limit. If you could have both, you would boost your signal. This one is a bit stronger.
And maybe I can ask another question. So in the formula, there's actually like a similar length in terms of the geometry between the distance of the source and DL. I suppose is a length indicate. It's like a.
It's DL is the distance to the lens. So the distance to the CGM.
Okay.
The intervening CGM.
I'm just curious. Can we use that and then try to enhance? Because, for example, the number of images also is a square of this, right? So if there's it means that there's an optimal configuration to enhance. Okay.
It's halfway.
Okay.
Right in the middle is what you maximize this step.
Okay.
You have the source, the observer, and then your lens or your halo or your CGM. In the middle is the perfect configuration, which is what I'm using in the default or fiducial calculations.
In the cosmological scale, what distance is this? This is angular diameter.
Distance about 1 gigaparsec.
So I guess I was asking what kind of distance is it? Is it angular diameter distance?
Yes.
Okay.
That's correct. Yes. Exactly.
So a bit of a kind of a deviate from the scintillation scattering idea. So, but when you have a magnesium 2 clouds, you also increase the DM.
If they are high density, yes, the total DM along the path length.
But,
yes.
Is there calculations on by how much we are expecting the DM to increase?
Not specifically for magnesium. I think there is, because basically I think we are at the stage of treating one intervening galaxy one number for DM, or like 50 plus minus 20 for one galaxy in between. So no one has looked more precisely on, what if you hit it more toward the center and then you hit magnesium, how that changes.
See, I guess it sounds like based on this scattering calculations, I guess it's sensitive to the peak of substructures in the CGM.
Yeah.
But then DM might be similar to sensitive to just the total columnist.
Yeah. So I think even if you have, for example, so you will have the DM from the host, the DM from the Milky Way, intergalactic medium a little bit, and then intervening galaxies. If you hit 1 or 2 or 3 or 10 dense clouds, you will have a peak in the end. But I think it will be so tiny and so concentrated that it will not affect much the general. So we would not observe many FRBs, and one FRB will have a spike. It will be within the variation, because it's very small region.
So another question. So how are there other ways to suppress the scintillation? So for example, multiple layers of gas in the Milky Way, could that also introduce the suppression?
I think so. Yes, I think so. It's also possible that the host galaxy of the FRB also has scattering and has the same effect as one intervening halo. So that's a very good point. So all this blah 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 that I said, it's assuming that nothing else kills scintillation, which is not true, because several other things can kill. If there is diffraction somewhere, it can kill it. There is also a lot of instrumental effects, so you have to be very careful what you measure, because systematics and stuff can also kind of simulate or give you something consistent with no scintillation. So you have to try to have these things under control. Or our goal is, like, if we have a very large number of FRBs, then these things that are sometimes yes, sometimes no, will not be very important, and this will be isolated as the main contribution. But yes, on a case by case basis, there can be other processes. Yes.
There must be some statistics from pulsars, right? Do you know?
Most of them scintillate.
Most of them. Okay.
Yeah.
So that's
If you
promising.
pick a random sightlines of the Milky Way, and you have a pulsar, you will probably scintillate.
I see.
Right.
So like the 20% not scintillating, there's something going on.
Yeah.
Okay. It's good to know.
Hopefully,
Yeah.
which is not the Milky Way, but it might be the host galaxy. I think the host galaxy can play some of a role, so that might give us less strong constraint, more like a limit. Assuming that the host galaxy does not contribute much, then this can be the intervening.
Any questions for Lluís? Okay. If not, Lluís was still I think Luis's flight is tomorrow afternoon. So if you'd like to chat with him, either later today or catch him early on tomorrow. Okay, and then there's still a sign up sheet you can, or you just come to chat with Luis. Let's thanks him again.